started. We're not going to have any more modules. So the 9 that have been assigned so far, that's it. So just as you plan, when and how you're going to get however many you might get done. There's not going to be any more. I have tried to clear out my schedule as much as possible for the next couple weeks, so I should have even more time than usual, much more time than usual available to meet. So please do meet with me. I would be very happy to be just meeting with you all day, for 2 weeks. I mean, that would be a lot, but if it can help you get stuff done, that'd be great. All right. So, okay, so we're not having any more modules. So in some sense, the stuff that we're going to do now, it's not going to be on modules. So why should you come to class? I mean, because I'm fun, of course. But also, so what we're going to talk about, graph theory. And even though this is not going to be on any module, graphs are something that come up a lot. I know most of you are signed up to take algorithms with me in the fall. And we're going to be doing, probably half the semester we're doing stuff with graphs. So the more that you can practice thinking about them now, the more familiar you'll be to do that. And even if you don't take algorithms, just graphs are one of those things that come up all over the place in lots of different applications. So it's a fun thing to think about and a useful thing to think about. So yeah, we're just going to have some fun learning some things about graphs, explore some both kind of applications and some historical ideas of how it developed. All right, graphs. And when I say graphs, I don't mean this kind. Don't mean that kind of graph. Those are nice, they're lovely, they're useful. Not what we're talking about. I don't know why mathematicians use the same word for two completely different things, but I don't know. The idea of a graph is a way to model relationships between things. So relationships or connections. Right? And I mean, if you think about, I'm sure you can all come up with tons of real world situations where there's different things and they're related somehow. There's connections between them or relationships between them. Right? Think about cities and roads between them. Think about users on some kind of social network. Think about different maybe different configurations that a robot could be in and the different movements it could do to get between different configurations. Right? So, I mean, I can think of others, I'm sure, but some are pretty concrete, some are abstract, but this idea of having connections, relationships between things comes up a lot. And the idea is we want to be able to study those kind of situations mathematically and distill, it's like if we just think about the connections themselves, what can we learn about it if we kind of abstract away from the details of the situation? So that's what we're going to do. So let's define them, actually, and then we'll look at some examples. So a graph on G, and we usually think of it as a pair of two things called B and E. So what is it? It is a set of vertices, B. So B is the set of vertices. Sometimes we also call vertices nodes. The same thing, just different word. And a set of edges, E. Okay. Each edge connects two vertices. And those two vertices are called the edges definition of the graph just has to do with what are the vertices and which ones are connected. It doesn't really matter how we, so we can move things around and it's still the same graph from abstract point of view. All we care is how things are connected. And you know, there's actually lots of different, slightly different definitions you can give for different kinds of graphs. I'm not going to bother like writing formal definitions. I'm just going to mention some of the variants that we sometimes use, and it really just depends on the problem and what kind of things we want to model, like what we would allow and what we would not allow. So, for example, sometimes we allow multiple edges and multiple distinct edges between the same two vertices. I mean, and sometimes we don't. Let's say it. Right. I'll just say and sometimes not. It really just depends. Like this definition that I wrote doesn't say anything about whether there can or can't be multiple edges between the same two vertices. I mean, I guess the way I've written it, it actually does allow that. Because it doesn't say it can't be. But again, it depends. So, you know, this graph here, it kind of depends on what the edges mean. So, like, if an edge means it is possible to get a direct flight between those two cities, then it doesn't make sense for there to be multiple edges, because either it's possible or not. So there's an edge or not, but we wouldn't have multiple edges between the same two cities. On the other hand, if the edges represent specific flights, then sure, there could be multiple edges, because there could be multiple different flights between the same pair of cities, right? So, you know, I'll just draw like a dotted line here, just to show that, like, sometimes we allow that kind of thing and sometimes we don't. Sometimes we allow an edge to connect a vertex to itself. Right, so like, you know, we could have like a little, we call these edges loops. Right, sometimes we want to allow loops and sometimes we don't. So maybe right, in our like plane analogy, again, if we're just thinking about like kind of commercial flights between different cities, then obviously you would never have a commercial flight that like takes off from New York and lands in New York. Doesn't make any sense. However, if you're just talking about like flights in general, I mean, lots of private planes will take off and either like you go up and you do some sightseeing and then you come back down, right? That's actually a normal thing. So again, it just depends on what we're modeling. Do we want to model things that connect something to itself or not? And then sometimes edges have a direction. And this leads to something called a directed graph. Right, and sometimes they don't. I'll give you 5 guesses what that's called. It's an undirected graph. Right, this one I drew here looks undirected because I didn't really draw any little arrows on the edges or anything. But I guess, you know, if these edges are representing specific flights, then maybe they should actually have a direction, because it's like, well, this is a flight that goes from San Francisco to LA, so we'll draw it like, and typically we would just draw it like this, like with a little arrow, to show, you know, this is a directed edge. The directed edge, this is a loop, you know, this is like multiple edges. So again, right, sometimes the edges represent processes that have some specific direction or some kind of relationship that's directional, right? So you could also imagine like let's think about social networks, right? Sometimes they don't have a direction. Like if you're, friends with someone on some platform, it's maybe like it's a bi-directional thing. It's like we are friends, we are just connected. But sometimes, like on Twitter, you can follow someone. That doesn't mean they follow you. So those edges would have a specific direction because it makes a difference. Like it goes. Okay. Right, and if an edge has a direction, then we think of an edge kind of as an ordered pair of vertices. Like there's a first vertex and a second vertex, and it has a specific order. Any questions about any of those things? Anyone think of any other interesting scenarios that you might model using a graph, other than the ones that I mentioned?
Would a binary search tree be a graph?
Yeah, a binary search tree, any kind of tree you could think of as a graph, for sure. It's a graph with various special properties, right? But yeah. What else?
Could you consider neural networks to be graphs?
Yes. Neural networks definitely are graphs, right? You've got a bunch of like neuron node things, and they're connected to each other in certain ways. Yeah, that's absolutely a graph. Yeah, sure.
Every graph has multiple different, represent different types of relationships. Like in this example here, you might have a set of mountains that block off paths from crossing over them. So you represent that on the graph in some way. What's the graph show more than just the one thing?
That's a good, yeah, and actually let me mention, maybe I should have mentioned this already. Sometimes, so the way you would do that is I would say that an edge isn't, so as I've drawn it, edges either exist or not, but we can also kind of put some information on an edge and say, well, this edge is kind of labeled with some information. So you can say, well, here's an edge, but it also has a label that tells us what kind of relationship is specified. Or sometimes edges are labeled with extra information. Right, so that could be like the type of relationship. It could be something like a distance or time. Right, so maybe we would want to, in this graph, maybe we want to label each edge with how long does that flight take, or how many miles is it, or what type of plane is on that. Well, I don't know. So yeah, that's good. Good thought. Anything else? Did someone else have their hand up? Yeah.
Does a vertex have to be connected by edges, or can it be like
Yeah. That's a good question. So, what do you all think? So could I have a vertex that doesn't have any edges connected to it? What's the definition? What do you think? That's the head shaking. What does that mean? That means no, you can't have that, or it doesn't have to be connected?
I would think that you can't have a straight vertex because the definition states that a vertex has to have two endpoints.
That's an edge that has two endpoints, right? So an edge has to connect two vertices.
You can't just have a string shaking in the air.
Yeah, I can't just have there's a plane over here and just flying around, but it's not going anywhere, okay? You can't just have an edge that's by itself. But, does that say anything about whether vertices have to have edges connected to them? So, no, it doesn't. There's some vertices. There's also some edges. The edges that I have to connect two vertices, have any commercial flights coming into it, so it's a vertex, but there's no edges. Yeah, and because, sometimes that's an important thing to model, that I have these things and there's relationships between them, but maybe there's this certain thing that isn't related to anything. If that's the case, then we want to be able to accurately model that. So there's no particular reason to. Now, again, sometimes, depending on what we want to model, we might specify, okay, no, we can't have any of those vertices because we don't want that situation. But that would be something we would decide. There's nothing in the definition of a graph that would prevent that. Good. Is there anything else? Are there scenarios you can imagine that would be modeled by a graph? Yep.
A relational database.
Yes, relational database. So you could either think about it at the level of each table as a vertex, and then the edges specify like, what do you call, like, when you have like foreign keys or whatever. You could probably also think about like individual rows as vertices and somehow they're connected. I don't know, but yeah, for sure. I guess, yeah, maybe that reminds me, like, you could also think about if you have a bunch of classes or files of code, and you could think about like, or even just think about each vertex being a function. And like if a function calls another function, you could make an edge, right? That would be an interesting graph to look at. In fact, literally, like I know this exists for Haskell, and it probably exists for other languages. There's literally tools you can use that'll read your code and output a picture of that graph so that you can like get a sense of how your code is laid out, or like so. All right, we'll probably think of other examples as we go, and certainly more questions are welcome. But I want to talk a little bit about some additional terminology. So one of the things about graphs is that like there's more so than a lot of other subjects, there's just like tons of terminology, like terms for special kinds of graphs or special parts of graphs, whatever. Because all these things do come up so often, it's nice to have special words for talking about things, but it is also kind of a lot to take in initially. So obviously, I'm not asking you to memorize all these, but it's nice to be familiar with them. It's like, oh yeah, I remember that word means something about a graph. You can go look it up. So here's some graph terminology and special graphs. So we'll just say, let G equal to E. And for now I'm going to talk about an undirected graphs, meaning that edges don't go in a specific direction, they just connect things. Okay. So let's see, definition. If I have two U and V, which are vertices in my set of vertices V, they are adjacent. If, aka neighbors, yeah, not only is there lots of terminology, there's lots of synonyms. So I don't know why, but if U and V are endpoints of an edge, okay, and we also say that E is incident with U and V. Okay, so up here in this example, right, San Francisco and Denver are adjacent because there's an edge that connects them. San Francisco and Little Rock are not adjacent. It is possible to fly from San Francisco to Little Rock, but you'd have to change planes, right? So they're not adjacent. There is something else that they are. There's another term that talks about that idea, but we'll get to that. number of edges incident to it. Okay, but if we have loops, we're going to say that loops count twice. Okay, so it's literally, if you look at a picture, it's literally like the number of lines coming out of it. Even if some of them happen to like connect back to themselves, you can count that twice. I mean, in some sense you wouldn't have to, but it's one of those things where like there's a lot of theorems and things and algorithms and stuff that just kind of work out nicely if you define it this way, and otherwise you'd have to have special, you'd have to say like, well, but for loops we have to have a special. So I don't know. Let's see. What's the vertex on this graph with the biggest degree? Chicago. What's the degree of Chicago? Looks like 4. 1, 2, 3, 4. If these dotted things are here, like New York also has degree 4, right? 1, 2, and then this thing counts twice. 3, 4. If the dotted edges count, then I think Denver actually has degree 5, right? 1, 2, 3, 4, and this is 2 different edges, so that those both count. Conway has degree 0. Degree 0 is another way of saying it's not adjacent to any other vertices. It's kind of just off by itself. Okay. All right, and let's. I'm going to explore something, and we'll see if we can prove our first kind of theorem about graphs. So let's look at some examples. I'm going to look at. We're going to look at the sum of all degrees. Which, why? Why would we do that? Well, turns out to be interesting. But let's just make some example graphs, and we'll see kind of what the sum of all degrees is. Okay, so here's some example graphs. And then I'll just go put one in each box. Here's the degree sums. Just making some boxes, just so we can like tell what's part of what graph and what's. So I don't know. Let's just. Is this a graph? Just one vertex. Why not?
Because there are no edges, and a graph is supposed to be a set of vertices and a set of edges.
Okay. And is there such a thing as an empty set?
Yes.
Okay. Yeah, so you're right. There has to be a set of edges. I agree. But the set can be empty. So, yeah, this is actually okay. So yeah, that's a graph. In fact, you can have a completely empty graph that has no vertices and no edges. Not that useful, but I mean, that's a thing. 0 is a number. Empty graph is a graph. Let's do something. So if this is a graph, maybe I'll make this. This is a graph. It's got kind of 2 different pieces that aren't connected to each other at all, but that's okay. This is part of why I put them in boxes, because otherwise you wouldn't be able to tell, like, is this 2 separate things or is it one thing? I look just something really crazy. So I have like a pentagon thing going on. Which incidentally, right, like the way I've drawn this, these edges cross here, but I didn't put a dot there, so I'm not thinking that there's not a vertex there. The edges just happen to cross each other in the way that I've drawn it, but that doesn't, who cares? The way that it's drawn doesn't matter, right? The only thing that matters is which things are connected. So, all right, so what's the sum of all the vertex degrees in this graph? The first one. about this one? 2. Yeah, this vertex has degree 1 edge coming out of it. This vertex also has degree 1. So, you have 1 plus 1 is 2. How about this one? So, 1, 2, 3, 4, 5, 6, 7, 8. Yeah. What about this one? 4. Okay. This one? Let's see. This is 1, 2, 3, 3, 3. So 3, 3, 3, 3, and then a 2. So that's 12 plus 2 is 14. Okay. Anyone notice any patterns? We can also make some more graphs if you. Let's see more examples. Get some different simple graphs. So, what's the degree sum of this one? 4. Yeah, 1, 2, 3, 4. This one? 4. Also 4, right? How about this one? 4. 4, okay. Let's do another triangle. 2, 2, 2, 6. Yeah.
So is the degree always twice the number of edges?
Okay, that's an interesting guess. What do y'all think? Does that look true for these ones that we've seen so far? So Mason's guessing that the sum of the degrees is always twice the number of edges. How did you come up with that?
I guess it's the nature of the edge itself, since it has to have 2 endpoints.
Okay.
It'll always make it'll always add at least
Yeah.
each endpoint will add 1 degree to the vertex.
Right. Okay, so you're actually already proving it. I was just asking like how you came up with your guess, but yeah. No, sweet. Yeah, so you're absolutely right. And I like that way of thinking about it. So let me see if I can restate it. And make sure everyone understands. So this is really kind of a combinatorial proof. We're kind of saying that, so the theorem, this is called the Handshaking Theorem. Let's say, let G equal VE, an undirected graph. And the sum of all the degrees, the sum over all the vertices of the degrees is equal to 2 times the number of edges, the size of the set of edges. Okay, and the proof, right, is what Mason said. Well, so one way to think of this is, well, we're just adding up all the degrees. But another way to think Well, look, each edge has two endpoints, and each of those endpoints adds 1 to the degree of that vertex, right? Even if it's a loop. Now, this is part of the reason that we define loops that add 2 to the degree. And so, well, if every edge, right, and of course, every time you add 1 to the degree of a vertex, it makes the sum go up by 1. So, if every edge contributes 2 to that sum, then we'll do 2 times the number of edges. So, the proof is every edge contributes 2 to the sum on the left. One, or let's say it adds 1 to the degree of each endpoint. It's called the Handshaking Theorem. I guess because you could think of, if you think of the graph in terms of each vertex is a person, like you're at a party or something, and like every time you shake hands, that's an edge. There's an edge between two people that shook hands. And you know, if we go around at a party and you shake hands with some people, and you just keep track of how many times you've shaken hands, right? And then at the end of the night, we add up, you know, you just look, okay, how many times did you shake hands? 4. Okay, how many times did you shake hands? 2. All right, we just add those all up, right? It's going to be equal to 2 times the number of handshakes that took place. Because every time there was a handshake, that was 2 people shaking hands, and they each like added 1 to their total. Here is something that we can prove pretty easily based on this. An undirected graph has an even number of vertices with odd degree. So in other words, you can have lots of vertices with all sorts of different degrees, but if you look at the vertices that have an odd degree, like degree 3 or something, then there has to be an even number of those. So we can look up here for some examples. So like in this graph here, this vertex and this vertex, these two on the top have odd degree, right? This has degree 1, and this has degree 3, right? And there's an even number of them, there's 2. These ones both have an even degree. In this graph, all 4 vertices have an odd degree, so that's even. In this graph, right, it's these 4 that all have degree 3. The other one is even, so there's 4. Right here, it's these 2 that are odd. Both of these are odd. And this has none that are odd, right? So why is that? Well, let me just ask you. Any ideas why would that be true? And I claim that, well, you know, it basically uses this fact that we just proved. Right, so if we add up all the degrees of all the vertices, are we going to get an even number or an odd number? Is that even? Why?
Sorry, wait,
Yeah, it's 2 times the number of edges, right? So even. Okay. So every time, let's say that I do that, I get an even number. Now I'm going to take away a vertex with an even degree. Say, forget about that one, let's subtract that. I'm still going to have something that's even, right? Because if I take an even number and I subtract an even number, I get another even number. So I can take away all the even vertices and I'm still going to have an even number. So in other words, if I add up the degrees of all the odd vertices, I have to get an even number. Well, if you add up, the only way to add up a bunch of odd numbers and get an even number is if you add up an even number of them. Because odd times an odd is going to be odd. So that's it. So, you could write it a little more formally, but that's basically it. It's a proof. So we could say let V0 be the set of even vertices, and V1 is the set of odd vertices. Then we know that 2 times number of edges is equal to the sum of all the degrees, which is equal to, I could split this up and say, well, this is just, the sum of all the degrees of the even vertices plus the sum of all the degrees of the odd vertices. Since the sum of all the, or actually, let's do it this way. Sum of evens is even. So, hence, this must be even too. Because they add up to something even. And then we say, but the sum of an odd number of odd numbers would be odd. So there must be not earth-shattering, right? But it's one of those things where like this might not be the kind of thing you would think of if you're thinking concretely about like flights and whatever. To be able to step back and say, okay, wait, it's just a graph. What do I know about graphs? Oh, I know some facts about like degrees being even or odd. And maybe that might let you conclude something about, I don't know, it's hard to think of a really practical application. This doesn't tend to have that many like directly practical applications, but it certainly comes up a lot where you're proving other things about graphs, because you can say, well, I know that like this graph can't exist because it would have an odd number of odd vertices, and that's not possible, right? Things like that. All right. What I want to do next. we have one up here. This one. Yeah, but fundamentally, it's always going to look like that, like some number of those things. How about all degree 2? Is that possible? Yeah, Grace. What does it look like? You just think it's possible? Mason?
You can make any like polygon.
Okay, so like, yeah. Yeah. So this is called a cycle. We usually don't use the word polygon just because polygon has to do with like specifically what it looks like when it's drawn. We don't actually care about that on the graph. The point is just that things are connected kind of in a cycle. If you keep following edges, you would get back to where you started. Yeah, so any cycle like that is going to help. How about all degree 3? Put it over here. It's a little more interesting. Well, maybe not if you have one in mind.
If you just put a vertex in the center, and then just connected all the other vertices.
Like this one? So I think you're on the right track, but I think that doesn't quite, because the problem is the vertex in the middle has degree 5.
Yeah.
But can you fix it?
You just make it a triangle.
Okay, yeah, so if we start with a triangle, it would still do the right thing with all the outer vertices, like Olivia was thinking, but then the one in the middle is also going to have yeah. There's actually lots of these that you can make. There's lots of different graphs you can make for they all. Okay. One more question for you. Do the degrees uniquely determine the graph? So in other words, if I say I'm thinking of a graph and the vertices have degrees, 1, 1, 2, 3, 5, and 6, or something like that. Is there like only one specific graph that I could be thinking of, or is there a scenario where there's two different graphs that nevertheless have all the same vertex degrees? So I'll also say suppose we have two different graphs with all the same vertex degrees. Here.
I guess part of the question would be like, in terms of how you define what is one graph and from another. Like if you think of just like
Yeah.
1, 2, 1, is there a difference between like a V and an upside down V,
No, yeah, there's not a difference in terms of how I draw it. So that's a very good question, and you're right, I haven't really defined that. I can define it formally, but like, what would be an informal way to define that? Basically, two graphs are the same if there's a way to label the vertices. So like, the label is like the vertex in this graph and the vertex with the same label in the other graph, everything looks the same. Like if you stand there, you're like, I'm connected to exactly the same other vertices. Or you can think of it another way is take a drawing of the first graph. Can you like move the vertices around and bend the edges around so that it eventually looks exactly like the second graph? If you can do that, they're the same. Otherwise, they're not.